I'm already late, so let's get started. As is usually the case, got my trusted bottle of tea that will keep me through the night and more. So we should get started a bit. And compile. Here is where we were. Dante. So I had a few questions last time that I wondered out loud. So I'm gonna answer a few questions. So one of them is sequence core. That would be this paper. But you probably can't see anything. Yeah, that's the paper. The other interesting paper is this one on supercompilation. Okay. That's the reference, some of the reference I'm going to mention. There's also compiling by continuation. I don't have a link right now. I can add one later. It's a book by Andrew Apple, I believe. Okay, let me backtrack a bit. So there was one of the questions I wondered is, okay, so I wrote a language like this, and this is sequence calculus, and that means in particular that there's a bit of symmetry and there's no obvious stack. So the value here is what you want to use as a stack. At least when you use a command like this, you read the computation as something to compute and the value as a stack against which to compute it. It's not the only way to think about it, but let's think about it this way. And the problem is that here, like call CC is trivial to implement. Like it's just a new project. No, it's a sidetrack while I'm I'm purposely thinking of something else. As part of this project, another part of the project. The idea is, because as part of the peppermint story, or at least the refined experiment story, I want to be able to use a normal compiler on a normal language and do some optimization as part of the entire thing. It's kind of the allure of that approach, to not have to do extraction and just have a normal programming language, an uncompromising programming language. So this is a part that I absolutely don't need anytime soon, but because I was a bit in a rut and I couldn't really produce progress rather. I was trying to progress and I was a bit blocked. And so I thought, yeah, let's do what I usually do when I'm blocked. Like, just think of something else for a short while and hope that ideas come to me while I'm thinking of something else, which is usually the way they work. And to be completely fair, I got some ideas, at least. I understand my problems better. I'm not as stuck as I used to be, but I want to see this through for the time being. And on this other page here, I listed a bunch of interesting distractions that we can go through when I don't have progress. Here you go. So it's in the repository. Well, it's in my branch right now, but the branch is in the repo. It's gonna be there somewhere. So these are the sort of things that I have in mind right now, like doing something a bit silly and a bit easy, like a little easy, but not too much. So anyway, this is sequence calculus kind of thing, system L sort of thing. Like what I did in my this section of Veil paper, like Airline Korean 2000. And brain not working right now. Yes, so one of the difficulty is that basically one of the essential objects is capture continuation, and you can't really make this computation work without it. Like the CC shows in a number of like in application you have a CC, that's how you implement it. So I was like, okay, that's very expressive. It's very easy to represent abstract machine commands in it, which is kind of cool. But how do I lower that to a like low level language? How do I make use of a stack? So how do I lower this language? Turns out this is not harder than using CPS as an intermediate form. Actually, it's much of the same thing with a more dedicated syntax. And so we have the same problems in compiling by continuation that calls CC is trivially representable. So the solution is both in compiling, it's not by continuation, it's compiling with continuations, sorry. And I forgot this S again. For anyone watching, French people are naturally immune against final S's. We'll learn not to think about them. It's a weird thing. It's because, so these plural S's, they come from French in English. The S for the plural. You can also find them in Spanish. Story for another time, but not Italian, for instance. But in French, they're not pronounced. Like almost always not pronounced. And so we write them without pronouncing them, and this sort of, they have this, in many of us, they have this ambiguous status that we just can't quite see whether they're there or not. It's a weird thing. Both in compiling with continuation and sequence call, we have the same solution, which is basically having a linearity constraint on the stat thing. When the stat is linear, then you have to use it syntactically as a tail object. In sequence call, they even only need a single stack variable. You can exploit this property. Oops. To lower code, to lower sequence code. So what I don't know though is whether we can do some type directed things. Just knowing that something is linear in the type, can it get us something much like normalization by evaluation can be type directed? I don't know. I think in Haskell core, lowering is very syntactic. You put something in a very in a form that is very similar to a normal form, where everything that might have to be shared is a let. So basically, what you need is that applications. When you have f of x, y, z, x, y, z must be variables. So you do this transformation in a Pascal core prep in the pipeline, and after that, you can quite easily lower it to STG, which is a language that is pretty much an abstract machine with just a tiny bit more nicer syntax. And anyway, so another question I was asking was oh yeah, so what does sequencall use let on commands for? So that was easy. I just had to read the paper. So first, they are not really lets of commands. They are lets of computations, with a small twist. Yes. Okay. I couldn't type a T for some reason. Full twist. They have a. They are variadic. In this tag argument, and are eliminated with a form of multicut. I can sort of show what it looks like maybe if I get there. So it's basically to represent, that's the wrong paper. I was not going to find it. That is much better. Ooh. That's around here. So instead of having a single argument, so it's to represent join points. I think that's a bit higher than this. That's a callback to. Here they are. So here you have the multicut. So jump J takes 3 arguments in that case. So it's cut against 3 things. And we have the syntax somewhere for creating one of these, maybe. Well, it's this one here. That's the mu. And you see that it takes 3 arguments. It's not very different from a single mu that would like take a tuple instead, I think, but yeah, it's presented slightly differently. It's used to represent join points. And finally, my question was, should the lets that we use in for the supercompilation be lets of values of commands or of computations? And the answer is quite straightforward, actually. The answer is computations, and that's because we want these lets to represent fixed points, and we only have fixed points, like in a polarized sequent calculus, we only have fixed point on computations. At the type level, there's sort of the least fixed point on values and largest fixed point on types, on computation types, and these are dual to each other. But at the term level, only computations can have a fixed point. You don't like if you take the type of list, and I mean list as in the data, not in Haskell, but in Coq, say, the type of list, it just cannot have a fixed point. Now you don't build a list by fixed point. I mean, you can make a fixed point over something else. You can have a function that builds a list that is a fixed point, but you can't build a list proper by a pure fixed point, like without an argument to recurse over. Like when you build a list, it's just a succession of adding one thing to the list, and that's all. And you do that in a way finitely many times. Like there's more like an ordinal number of times in practice, because you can have like context, and so these can correspond to ordinals. But the point is that if you're iterating over something, it's something else, and it's the computation that does the iteration. So it's kind of a no-brainer there. But before we start on this, let's just push this. Before we start on this, we're going to make a few adjustments. First, I'm going to change my smart constructors to be a bit more opinionated. So I'm going to make 2 sets of them. CBN, CBV. This is going to break everything, but so basically the goal here, by the way, is just to supercompiler. To recap, is just a way to, it's a way to do an optimization by partial evaluation, basically. And so here we have here something fairly direct, which is like const of A, B, and it computes B. Like it's slightly more complicated things still compute, and we can see that we compute under lambdas. Lambdas rendered as a mu of a pair after it's been interpreted, but I can still write lambdas because I have smart constructors for them. And yeah, so these are a couple of tests. And sort of one of the cool thing about supercompilation is that it's supposed to be able to do some fusion. So one of the goals today is to be able to do fusion. There's a couple of things to do first. So okay. So here, computation to computation, that's good. But here I want computation to computation to computation, because we're doing CBN. Now it's not going to be good. So what do I need to do? I need, so that, I want to call it, okay, I'm going to write it there. It's a bit weird to write it U. What was the... I don't remember how I write my up arrow. That's funny. Let me check. Boom, 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 boom. Okay. That's sorry. That's the down arrow. Okay, up arrow is this one. So now we don't evaluate the U thing because it's called by name. So here we have to do what was it? A thunk. What's the name of it? That's a value and it's case return. And that's not quite correct. Yeah, actually, let's write it correctly. So that's not that's supposed to be return, but that's not a return because so that's a new okay. I'm already lost in my own paradigm. Yeah, actually, it's just that's the thing. I think. Is this correct? Yeah, I'm pretty sure it is. Yeah. Yeah, that looks correct. So, what was the name of this again? Case return. Thank you. Case return of interact. So again, we have the computation here, so that's U, and you have the value here, and that's var0. Okay, and we're completely done. Here we want a computation as well. And on a computation that returns a value. So my one here is var0, and before we call all this, we do case return. It's hard to write. It's definitely not var0 here, because it's within a CC, right? Right, so that's var1. Another variable. So that's the one here. So case return $interact. I don't think I need the CC actually. Let's see. I used to know all of this. It was my shtick a few years ago. Okay, we're starting very peppy. I'm saying more than words. So I want a case return first, that's for sure, because I want to force V before I do anything. So now, which I should call U now. Even if U sounds like a value name. So now in var0, I have V, and that's what I want to interact against this. But this is a CC interacting. So really I can just remove the CC and put var1 here, yeah. It's not happy because something couldn't match type. Oh, case return. Oh yeah, case return is a value. Oh yeah, there's no U. I want to do interact. And now I need my CC here. And now I realize that my variables are wrong. What? Okay, that was painful. And we want var as well. Because here var is non-obvious. So I think I'm going to skip on the CBV versions for now, and we're going to just do call by name and see the CBV later, because I spent too much time on this. Here, what is exactly that I want? Like lambda XX. So X there. I think there are some lifts missing here as well. Oh, there's everything's wrong. That's var2, that's var2. Why did anything work before? Okay. So x continuation and returns echi. That sounds legit. Because everything, so this must be, so this is a thunk. I want to make a thunk into a computation. So cc var interact. No. Oh yeah. I need a return of sorts. So what we're doing here is x, let's say it's a variable name, to mu k so oops it's hard to type. That's the variable evaluated against the environment. Basically expects x to be a mu aparo k, and so it will just say like run the computation held by x. That's just false. That is just force, I guess. And we should probably just make ourselves a force thing because that would be easier. Well, I guess not. That's not very useful for now. It takes a value, returns a computation. And here, what you had is we have a computation, so we need to make a value for its continuation. Case return is the continuation. Just says what is the result of my value. Because things are used left and right, it's a bit confusing. It's fine. Now we have to no more flight check errors. Of course there isn't. Oh yeah, these are not type check errors because they're in the command execution thing. So Oh yeah. We also need smart constructors for symbols, I guess. And the type, what I wrote before seemed like it was incorrect. I forgot to write what that was. That was a string, yeah. That was the other way to represent. Well, I guess it worked for that particular example, but string to computation in that case is just it's easy. It's return of simp s 556. Okay. Okay, it does what it's supposed to do. Here is the same. What? It was funny. It just jumped. R1 sim. It does what it's supposed to do. Case here it's just var0. Whoa. Small sim. There's more going on here. Lam, small sim. Yes. And here we are. It's probably good. I don't remember how to read this. It's a bit easier to read though than they were before. So we say case X. That's what's happening. And then on the first case we have lambda. That's the identity applied to the constantly b function, which I'm not seeing right now. Oh, that's the second case for some reason. Oh, sorry, there's identity on the first thing and constantly b function on the second one. So is that the identity? Well, one of these is wrong. This one says 0 and this one says 2. Oops. For the continuation stack, 0 sounds wrong. Might have messed up this. But that is weird because it's the same one both. Case I minus 1, right? Yeah. Ooh, this is big here as well. That's not a good sign. It's way too big. There's variable 4 here. These two are good. We haven't started doing the actual thing. That's the thing that I thought would take 15 minutes. Took more. It's not done yet. Here the goal was U, E1, E2, and we generate. So we first have to evaluate u. So we set mu k. So that's the current stack. And here we first evaluate u. That's u here. And we do mu and k r, let's say that's the value of u. And we do another thing, and we evaluate r against it, and here that is mu. Sorry, that's the this one, mu 1 dot x and in that case I've got x is a thunk. X the thunk. That's kind of what I missed, I think. So here I want force x against k. In oops. Okay, so now I want to do force. Actually, I don't need to do this. No, I don't want to do force x. I want to do. No, I've got to. No. That's not true. I've got E1 here, and I've got E2 here. And E1 captures x as its first variable. That's correct. That looks fairly correct. So 1 here, 1 is the value of r, and I don't reference it. That's normal. I only use it here. That's 0 here, yeah. That's the value of u, and I do the case against the value of u. So here is 2. It looks very, very correct. Something is off. Maybe application is off. This one I haven't changed. This one, pretty sure is correct. And variable I can get my variables by application. And by case I get, but I haven't made the constructors for the disjunction yet, so that's fine. So here then I have the variable. Oops. That's a suspended U. When I get the variable contains a value like this. So I get U against K. And that's what I want, yeah? I'm pretty sure it is. So I push something, so it's a pair. So I put this on the current stack. I run against the current stack, yes. And so that's case return. Value. $0. This looks very, very correct. Everything looks very correct. Let's do something simple. It says for this variable that's a lot of mu's. To force it, and I get it. Something returns a value. Well, actually, that's correct. And the value is what I match again. This is not the most exciting of days. I'm going to do something a bit easier here. Too many vars. Sim A. Sim B. What I do? Whoa. I'm typing completely random things. Okay. Again, so here we have, okay, and 2 is inexistent. So there's something escaping. Why? Because here quite clearly, I have a 2 here, doesn't point here, doesn't point here. Have the CC first. So CC is replaced by unit and it's not properly. So there's 2 possibilities. Either there's a problem with my substitution function, quite possible, or I didn't count my binders properly, but I'm pretty sure I did. That's 0, 1, and 2. And so unit should be here and here. Was it here? This should be var 0. Let's give it a name as well, var x, like simp x instead. So that it doesn't get lost. Oh, it is. What? What? That's my var 0. Here the unit is disappearing and things are run. Oh, yeah, because sim is less block than var 0. But this is still not unit, and it ought to be. So let's try and figure this out, shall we? Substitution. Shift twice. Shift here. Case I doesn't do the proper shift. Here we go. It's called case I. Case I. That was easy, and I was looking in the wrong place all this time. Oops. Okay. That looks much better. But this is still horrendously huge. For reasons unknown. This one does case X. Return the identity. Why is there A and B here? Oh, here it is. Okay. Okay, the case is applied to A. Since this is the identity, I should see an A here. And here I just forget it, so I get, okay, that's exactly what I'm supposed to see. This, I have no idea if that's what I'm supposed to see. It's unreadable. Okay, we'll just assume that's what I want to see. So here we have lam a, and we have const cd, that should be a c, so we should have a lam c somewhere, and I see the d creeping up, which, oh no, that's not const, that's the second argument, okay. No, that's const, so there's a bug. That's fantastic. Huh? Because the D should be, because that is const. It says lambda x, lambda y x. I say C and D, so that should be C, but I can see D here, and there's no reason for it to leave to be anywhere now. I know that's under a lambda, but, or maybe I failed to enter under a lambda. Is there some obvious things? Oh, here. Look at this. This is not reduced. Okay, so there's some reduction missing. We can have a look at why. It's my splitter. My splitter is very simple. Interact E prime V. Well, we kind of see that it's something is missing here. Get a computation, and a bunch of sub commands. I don't remember what that means, honestly, though. I guess it just means that I'm not optimizing terms in any way. I'm just waiting for commands. That means that I'm not going very deep. Right, I'm only looking into the E. So what if I do interact here? And I do like value subs pure opt v. Wasn't sufficient. Make any difference? It makes zero difference, right? Yeah, it makes zero difference. Kind of shot though. Okay, I kind of feel that there will be a third time on this. We'll see. I have no idea why all these mu's are there. Like all these, if there's a mu here, it means that I haven't gone down properly. So what do I have? I have a return. So I think I see the problem. Here's the problem. Here, everything is a command immediately, except there, I've got a value. And because I've got a value, I say, oh, just pure. So I stop here. Instead of looking inside the value for a command. I'm not entirely sure what I'm supposed to do. I think I should recurse in values. Something like this. So where split values. So we're going to have all this, except that's value to value. And this one will be deep. I'm going to just look for the commands. Equal value subs. Or split value, really. Value subs underscore. I don't care about commands. I never have any right now. If I have a value, I do split value. What is the order actually? Yeah, so I do split value. There's an F here. I do split value of F on values. It's well-founded because of how values are always well-founded. That matters. And on a command, I do opt. And then here, I do split value. And here, I do split value. Of F. Of opt. Of V. Oops. Boom. Look at this. Whoa. That's one hell of a refinement. That looks fantastic. Now we don't have stray muse, which is exactly what we want to reduce. Actually, I think it's it might be all one rule for the time being. Maybe I have more. I don't remember what I put. Or reduction rules. Oh, I've got all the rules. So something obvious is obvious. And so we would use them. But at least the muse, they have to disappear because whenever they see something, they say, oh, I'm good. Muse are really just very temporary things. And actually there's a point in making a special case, like reducing all the muse very early. You're going to have a ton of them. And then at least you want to reduce all the muse before you do any analysis anyway on things like this. So, okay, that was pretty cool. Oh my God. And I completely lost track of what we're getting to do. So I need to add a let. Need to add a let. And let is, I guess, a command. It takes... it's a command builder, I think. command. Like, yeah, like let and jump. Where are they in the syntax? I don't care about the logical interpretation. Oh dear. We have jump. Yeah, that's a command. And jump is a computation. I think, and I'm not really sure. No, it's a command as well. That's kind of curious, but is there a short syntax maybe? Jump doesn't appear here, of course it doesn't. It's fine. This is definitely a command, so that's good. And here, okay, we replace jump by something, by C prime. Okay, so jump is a command as well. Okay, fantastic. Well, I think we're going to follow the same sort of idea. We're going to add to commands the ability to be a let. Let takes a block. So it takes a list of commands and returns and a computation and returns a computation. The idea is that this is a recursive let for the sake of our example. And we will need names as well. So let's will absolutely 100% need to be names and not variables. So we're not going to do this. We're going to do, yeah, okay. No, the binders are binders, but what we're going to do hello, Dr. Dog 4. Welcome. I read Korean, I guess. So we're going to need another notion of variable, which is, I guess it's jump, but we'll call it call. South Korean. I know James is still here. No, he's not. Anyway, I don't know anything about the Korean language, to be honest. Just what it looks like. I think I'd like to. You are? Okay. And you do speak Korean, don't you? String. No, you don't. Why do I think you... Oh, whatever. Let's talk about that some other day then. Yeah, I think Korean is a very interesting language. Okay. Very, like, the way it's spelled is very unique, and it's kind of cool. It makes me want to learn it, but, you know, you need to have priorities. Time is finite and all that. I call it lead. Could also be called deaf. Yeah, pronunciation doesn't look like it's the hard bit. It's the it's just, or like remembering all the letters maybe. I don't know. It's also not very useful on its own, just knowing how to read a language. There are languages that I know how to read and I don't know a word of, but it's... Yeah, reading Hangul. What is what language name? Oops. Yeah, the language I'm writing, right? The language I'm writing in is called Haskell, and it's a functional programming language with pure function types. And the language I'm defining may be called Peppermint at some time in the future, because yeah, I'm just playing around. So if you want to know about Haskell, ask. I can tell you things. James can tell you things. Let's see if I remember anything about my Haskell. Intercalate. So it's so that's in data list, right? It was fantastic. And that would be interact, traverse, yes, actually the level. But long history. Yes. So the history is a bit longer than this in a way. So there was a bunch of programming language researchers that were interested in so-called lazy functional programming, which I can explain what it is if you want, but that will take a while. Which I must say existed mostly for theoretical reasons, but because the theory was nice, people wanted to make them work, and they were very desperate. And then, like, there was, there were many languages that all did their own thing. The big one was called Miranda, and at some point, like, this community decided to try and work on a common language to to be able to push the features that they wanted into something more production ready. And so they decided to try and focus on Miranda. But the author of the Miranda language decided to not open source it, as I understand it. Like, I don't know the details. I was definitely not around. It was around the time where I was learning to read. So, yeah. But the point is, they were like without really a language, so they decided to make a language by committee. Was it? It's possible, but I don't know. Like, I haven't. Like, I don't know if Dave Turner is still active at all. That would be cool, but Miranda is a bit passé now. The point is, all these guys got together and invented this language called Haskell. And so that started in 1990, but the first official version of the language is from 1998. Fantastic. And yes, it's a very modern language in many respects, though it also has some history. So let num binds equal length ease in value. Yes, my modus operandi is that I play video games every other week. So during the summer holidays, I played a game of Braid. I hadn't played it for a long while. That is not on value, that is on command. And spoiler, oh yeah, that's because it's supposed to be let. Still not good. Command. What? Sorry. What did I write? Okay. So this like yesterday, or like during like 2 nights ago, the last DLC of Cadence of Hyrule was released. So that will probably be what my next stream is going to be made of. That's a whole new campaign, and it's a very good game. Okay. Sorry, I didn't get that last sentence. I'm a computer scientist, so... I think there's a typo or a word that I don't understand. Right, I'll bail on this one for the time being. I think we are going to want something new now, because our semantics will not be on commands anymore. Now we're going to get a bit closer to this thing where the splitter, I can find it. As type, yes, state to term to state to term. So we're only interested in commands, but we need a bunch more things. So what's going to be happening is, and whenever we found a let, we are going to store it somewhere. So there's basically two ways to do this. One way is to just imagine that we have a bunch of lets at the beginning. There's going to be I'm looking for my operational semantics. Here I saw it. It's called step. Let's go there. Come on. So here we say, okay, the constructors of computation, sure. So first, the idea is of sequence calculus is of command. Yeah, the names are silly. Okay, sorry. Here we go. Command has two constructors. So one of them is just define a bunch of, like, make a bunch of definitions. And interact, which is the most important thing. It corresponds to cut. Hey, David. So it corresponds to cut in sequence calculus, if you know what that is. And it just, and like from a, we want to think of this as an abstract machine of sorts. So we have something to compute and we have a stack that happens to be a value. There's a bit of confusion between values that you compute and stacks in sequence calculus, but that's on purpose. And so, you know, it's just like, you can think of that as the Krivine abstract machine if you know what that is. There's some term here to compute the value of some stack that is facing and they're interacting. So when there's an application, something is pushed on the stack. When there's a lambda, something is popped from the stack. And that's what we're going to see in our semantics. Now, now what? Now computations, they are these things that are not computed yet. There are, like, you know, descriptions of computations to come. And they're generally built out of commands. So they say, okay, a command is a computation that is defined, and a computation is something that requires a stack. And so this first argument says, let's name the stack. I called it CC for capture continuation as a reference to scheme. But let's name the stack, and then I can actually build something against it. This says, this is basically pop. It says, oh, let's imagine that the stack is a pair and name the two elements. Unit is really nothing. You imagine that the stack is empty and you can continue. there's a corresponding void that imagines that the stack is contains the element of the void type, so it escapes any computation. Case I says the stack is either 1 and something or 2 and something. So it's easier to understand as a normal case expression without the scrutiny. So you have either something of type either as your scrutiny, but the scrutiny is sort of missing. So it's a lambda case for the scrutiny if one wants. The stack is not actually a stack as you might see, because you have this things happening in pair of values. You can kind of make it into a stack, but it's not a real stack for real. It requires some effort to actually lower it to a stack, but it's doable. Some people have done it. And return a value. And return a value is just the trivial computation. It says, oh, I'm actually done. These are my terms. And then you can see this playing in the definitions of these smart constructors there. Like, so if you're doing a call by name semantics, everything is interpreted as a computation. So that's kind of nice. So you have a computation and you want to abstract over the first variable of it. So it's written here. We have u, and we want to write lambda xu. And we do that by saying, oh, well, let's pop the first value from the stack. And that is the rest of the stack, and then run the computation against it. Pop and substitute. And then when we see an application, we say, oh, let's name the stack and push u. So there's a bit of work here saying, oh, it needs to be a value. So I need to make a thunk. I need to make a closure for u because it's a call by value. It's called by name, sorry. And I push the thunk of u onto k. So that's a bit of a longish way to say make a closure. And yeah, that's pretty much the story. And then x, is a variable that holds a closure, so I need to call force on it, and that's the invocation for force. Does that more or less answer your question, James? Why does app make a closure? Well, it has a term. Like if you do app in Haskell, you have to make a closure for the argument because the argument is not. It appears a bit different in GHC, but the general idea, if you have a call by name or a call by need language, the U is not evaluated. So when you push it onto the stack, it needs to be frozen somehow, put together with its environment so that it can be resumed, etc., etc. So it's not a value. It's not an evaluated value. It's a special kind of value that contains code. That's what a closure is, for all intents and purposes. So I think we're going to use names. And so we're going to change the type of step a bit to say, so I don't know how to call it. I could call it state, or state. State is not a full name. It's a machine state nonetheless, so we can have to be very careful about what we're doing. Okay, state, and we have a list of string computation and a command. And now it's really a state here. And here we have a bunch of defs, and here we return a state. No, yeah, actually, state defs. So we ignore the definitions in most of these. Actually, let's do something. So these just ignore definitions, and we're going to add a new step function. That's cool. It does that. And the step we'll try to do state defs c step command c state defs. That's very Kabbalistic, but bear with me or go. So these are everything that ignores the let. And so now I can focus on the one that don't. It's not so much about partial evaluation as it is about call by name semantics. And call by value, you compute a value, so you don't need to compute a. But so I didn't do the smart constructors for call by value, but they will all do values instead, and then they would be inserted as a constructor using return. Not as a constructor, using a thunk. You make a thunk for the computation, and not the thunk, a return. Yeah, it's return. That's what I said. That's what I just said. That's what I said first. Anyway, so here we say, oh, if we can make a command step, we do that. Otherwise, we try this other function. And so it's going to be annoying, but okay. We have the definitions, and we have an x, call x. No, call x interact. Call x and v. In that case, we do state. We have the same d's, and we apply it to. Lambda e stay ds interact e and v, and the e is computed by just doing lookup x d's. It's not happy. Where is that? That's control applicative, I think. I'm on fire today. Right, that's wrong. Good. So that was wrong. That's my fault. That stands for a computation, not a value. So here, remove this and edit there. Indeed, that has nothing to do here. That's fantastic. Really? Oh yeah. So there's a couple of more to do. Changing my mind about something. I changed my mind about this. It really needs to be valued to be names, and we'll have to deal with shadowing at some point, but because these are not the same kind of variables. Yeah, it's a list of declarations. Exactly. So here, it's traverse of lenses. It's the coolest thing about Haskell when you think about it. So for those not following at home, this applies a function collecting some thing. The f is something that I collect. So I do that function on the list, and I say, oh, only on the second element of each pair. Just does the collecting for me. It's fantastic. I don't need this anymore, and I don't need this because these are not the same kind of variables. So, where were we? This has become interesting. I had, like, you know, it's kind of obvious in retrospect, but I had completely not anticipated this. So this is a possibility. Another possibility, of course, is a bunch of let of new decals, new defs, and C, and then we always progress by doing just new defs plus D's, C, and I need a let somewhere. Oh, yes. Okay. So reduce should be, I think reduce should return a, I don't know if it should return a comment or a, sorry. So the important point about these lets is that they're recursive. That's what makes the source work. State to state, okay. Reduce R change to be state to state. Okay. Terminate. We'll have to change standards. History is a history of state. So terminate history state. Shall I? Okay. Wow. So the thing is that here it's state to M command, right? It's command to M command by doing HC. Wait, no. Screech, screech, screech. Yeah, okay. Right, that's the one. So supercompiler is that one. And here we supercompile C, and so to make it reduce state anti-list. Boom. Still not happy. What's wrong? Oh yeah, split doesn't have the right type anymore. So that's state to command to state to command. Everything doesn't work anymore. So we are willfully ignoring the definitions for this split. Probably want to actually optimize the definitions themselves at some point. Let defs blah. Split value should have the same type. Ah. We have to decide how we do opt command. So I'm taking all the defs. That sounds unlikely to be correct. I have no idea what the bug is. Right, that's just my I wonder if I got this right. Variable non-scope F. Split. Quite definitely. Right, does a rebuild. So that's pure of let def c. So in this vision, all the definitions seem to sort of float out. Not entirely sure. I still have quite a few issues. The distinction between state and command and that word is very slight. You could possibly make it just that command has a single constructor. Not very interesting. I can match the first type, the expected type state with actual type command. Oh, it's the same again. I was supposed to write state here. Still not good. Yes, it is good. It is better. Oh yeah. Okay. Ah, this is more like it. We can almost write things. So are there other cases I care about? I think not. Okay. So, fantastic. So, what do we have now? We have a thing that can deal with lets in a bunch of ways. So what do we have? Like mu, let is define let on values before, but we need a let on computations that is recursive for this scheme to work. I'm not sure if we would have done with a fixed constructor and not that. I don't really know how that would have worked. At any rate, this is it follows the style of this particular compiler here, or optimizer here. So what's happening, and it's based on GHC in many respects. This is based on the experience that GHC has, and let being the recursive thing is the thing in GHC is used throughout the pipeline. So then we have a very small semantics, like it's a operational semantics, which is do reductions. In this case, we do substitution. In a better word, we might want to actually delay the substitution to be a bit more efficient, but that's just optimization of the optimizer itself. So we have this thing that executes one step of the machine. It's wrapped around by this that handles the lets that are recursive definitions. Which right now we never optimize, which sounds wrong, but one thing at a time, shall we? And what? And then the step function is called called in the reduction to like you compute a reduction, and from time to time you get stock and you split. You get to a value and you're good, and you say, okay, now that I'm in a value, how do I optimize further? And I look into lambdas and so on and so forth, and that's handled by this very small splitter. We need to make sure you terminate. There's a termination checker, which right now is we do only 100 steps, which is very weak. We can do much better than this, but this is probably beyond what we can do today. What we need now, we need to write something that has some recursion in it. I don't know if I can use several lines. So we're going to define map. Ooh, defining map. I want to do something recursive, so of course it's going to be on lists. And map, so it's a computation. It needs 2 arguments. So lam of lam. We do case. On the, so case on the second argument, so that's var 0. And if it's the first thing, we just we return unit, but it doesn't exist yet. And if it's the second thing, we do a case on var 0, which is a different var 0. I don't have a case, but I should, and I get a pair of things, and I return pair. That's a lot of things to define, actually. So that's, I've got 2 here, 3 for the case I, 4, 5. So var 5 is my function. I will soon want to make a named calculus or something. Var 5 in my function, I call it on, what here is var 0. And on this latter element, I call map again. Call map. applied to still var5 and applied to dear Lord. It's hard to write. Actually, that's var0 and the other one's var1. Okay. Now, interact. Let's just do call map and unit. Plenty of things. Oh, pass errors. That's not good. Okay, so what we can do is define let foo equals why there's one in particular? Oh, because I call it case. Okay. I'm going to call it case P. This is a weird reaction. There's still a type error, I guess. Parse error, no. Oh yeah. Oh. Oh. That's better. Not in scope case I. Why is case I not in small I? Okay. Let's be consistent then. Unit. So let's go. It was easy. Case P. Okay, this is going to be a bit more difficult. UE equals CC. Interact U. So again, we need to force U first. Then, so we have a case return here. Just quite the same. Here var0, because that's the result of the case return. And here we do, what did I call it? Case pair. Case pair. Case pair. Of interact of E and 1, 2, 3. There's one more than above because case pair finds two things. Pair computation. So here we have also, we need to force the computation order, pairs, when you compute, you need to choose which computation you do first, basically. It's just very sequential language. So here, we call interact. Sorry, we have EL, let's say. We're going to evaluate the left one first, for instance. So case return. So here there's 0. No, here it's I believe we do ER here. Case return. So now we have both of them. It's computation. I need a CC. So the second is what I captured in the CC, and that is 1, 2, R2. And here we have the pair of var1 and var0. Damn it. That is not okay. That is the wrong direction. That's the problem. This is a good point, because here it's return this. It's a computation. I need to return the pair. Good. Now we want call. This one is fairly easy. Takes a string, returns a computation. Boom. Yeah, it may be correct. Brilliant. Oh gosh, it's almost midnight and I haven't finished that part. No, it's not too serious. There's no optimization in map, but there shouldn't really be anything, I guess. I mean, that looks legit. There's even a 6. It's not very readable. There's a lot of muse, so if we only like simplified inside the map, we would get a much more readable function. Maybe we should do this. I'm not sure how we should optimize these, because like I could split here. When I split here, I could say what am I? here, we could say, oh, let me go into the depths first. I think, but it's not really what we want, because we would probably optimize them several times. What we really want to do is, whenever we add something to the context with step, we kind of want it to be optimized. I don't really know yet what we should do, because the problem is whenever I add it here, it can appear back here because of the call, yeah. But maybe it can't. It won't be able to because of the memorization in a minute. Maybe that's the thing. We'll have a look. But let's forget about it. Like, I can't think about it right now. We need to make something a bit better than this. So what we can do. Map on lam sim a, so we're going to replace everything by an a in the list. What does that do? Well, that is way more optimized, but still a map. Still has a mu too. That's because of the sort of silliness of all this. I just do 100. Maybe I should do 1,000 because otherwise, where's my terminator? Yeah. Ooh. Doesn't make a difference. That's interesting. Unexpected and interesting. Okay, I don't quite know why this doesn't reduce at all. Actually, there's no reduction whatsoever. Yeah, there's something wrong. Okay, I'm going to remove this later, but it shows something interesting because there shouldn't be a let inlet. Or maybe it just runs forever, and so because of that doesn't do any optimization. Where do I use my terminator? So when I get to stop, I do split, but then I don't do anything. Yeah, just split through, and every time doing nothing. But I should have the steps done full. So I'm not entirely clear why that doesn't work. Like here there's a call, so it should be what about if I do reduce foo? Okay. State. Mm-hmm. Okay, so step doesn't work here. Oops. Why not? Should at very least do this. But I should even... I wrote something wrong. So this is a bug. So all of this is blocked, so it shouldn't happen. I get to state, to the state devs, and I got state dev step command C, so that gives me a nothing. So because this is a nothing, this ought to give me a call to go, and go should see a let like here and answer just. Oh, it doesn't even go there. That's most curious. Oh wait, it did some reduction because it says just. It did something that put it exactly in the same state or something. So there's an identity operation somewhere on my thingy. Oops. That is much better. That is practically unreadable, but thing. Ooh. It's long. Oops. I may have to kill it. Maybe 1,000 is too long. Okay. Okay. Just check that there's no runaway thing going. There are many JC processes. Just one JC ID though. Okay. So optimizing this looks like it's a tad dangerous for some reason. I'm not entirely clear why. Definitions. I put 100 back, yeah? Value reduce the anti-foo. Get quite a bit of reduction, but not everything. Okay, yeah. Well, it could probably be better. But when I do optimize, it just crashes, yeah? For some reason. Yeah. I'm guessing there's a loop in there in the split. So split v. So we should go split, and like every supercompile should. Oh no. Go to different things. I go to smaller things. Same thing I revealed. There's something wrong that I do the let defs here, and that is quite incorrect. Because since I call the state defs later, let me have a look. Hmm. Hmm. I think the problem is that when we split, we might have a tendency to do to add lets and possibly to call ourselves recursively on whatever. No, I don't think so. It's still something weird, but oops. I don't want to do this memorization code today. We might still have time. See, here we add a ton of let blah. We might add a ton of let maps as well, and it's pretty big, so oops. Gonna have to study this. I don't know yet. I don't know yet. Something curious is happening. There's a bunch of things that are wrong. Because the problem that I'm seeing here is really since I'm just when I do things I'm putting the lead back here and I'm pushing the lead down. I'm duplicating. I really don't want to do this. But if I don't push the leads down, then whenever there's a split, I'm losing my devs, and that is bad as well. If I don't put the lead back, then they disappear altogether, which is just as bad. And that is sort of what I don't quite get right now. Should read that a bit more calmly. Oh. Okay. Hmm. I'm still here, yeah. Hmm. Smarter thing. So it seems to always split to simplify the LEDs there, but it doesn't. Right. If it pushes the LEDs down, then it just keeps it. So one. Okay. So we need to do that progressively. So first, we're going to not push the devs down at all for the time being. And here, I think if I do optimize, this shouldn't crash. Good. And we are going to remove this silly LED. So I'm just okay, so we're going to make a mutlet takes a list of string computation, a command returns a command, and mutlet of the empty list c equals c mutlet of something else equals let c. Okay, now I'm going to look for occurrences of let. That's fine because that can conserve the size. And here we're good. Here we do a mucklet. Here we do a mucklet. Okay. So now we have much fewer things to care about. And I guess we are going to also go down in the defs. So we're going to do split computation to f of computation, and that's this is not quite correct, but that will simplify my life a bit. Traverse to split computation. Yeah. I'm sorry. What did I do wrong? Ow. Huh? Oh, I get it. There's an 8 now. 1, 2, 3, 4, 5, 6, 7, 8, maybe. I'm not sure that there was not any closure. I probably miscounted, but why not? Even a 9. Oh, yeah. It's hard to know for sure. It's kind of weird that there's map several times. Oops. It probably unfolded some. No, it shouldn't have unfolded anything because I didn't give it any definitions for map as I was optimizing. Darn. There's 1, 2, 3. What is this? Okay, so there's 2 copies of map in the definition of a map and 2 in the body for some reason. Despite the fact that these guys don't have a definition for map. Well, I guess this one does, I suppose. So that's sort of what's happening, but this one sees an unfolding of map. I'm not exactly sure why map ends up that way, though. It is kind of weird. But map is not an easy function. So maybe, especially since like it's the call by value, the call by name map, sorry, encoded in call by push values. You have all these explicit force and things and sequencing. Still look weird though. Making a pair. I think what seems to be happening is that there's a case of case phenomenon happening. No, it just shouldn't be. So here are the 2 first functions. And here is the first case. So we say, oh, let's case the variable. And in a case where, oh, this bit of a, okay, that's, okay, we don't return the right thing here. It should be there should be a 1 and 2, which just make things more complicated, but we just return unit, presumably, in that case. Here's the thing. And in the second case, we're going to do like a bunch of things. So we force something. I'm not sure what that is. It's probably the var5. So we are forcing the function, which is now number 8. And then we're popping a value from the stack. And we're calling map. Why are we calling map? Well, something is happening, evidently. Oh dear. Well, we'll do a memoizer and we'll fix the bugs later when we have everything in place. Just, must confess, it's not very easy to debug. Like, it wouldn't be easy to debug if it was lambda calculus. Yeah, but that doesn't make things quite easier either. It's fine, it's fine. Yeah, we can also, like, things that can make debugging easier would be things like, where is my A, by the way? Like having a pretty printer. Okay, this is just there's no A, so this is quite definitely a bug. I'll take it slower. Okay, so what do we need for the memoizer? So here are the things. So we need a state, and the state we need the promises, all the states that have been previously submitted for compilation. So we give them a name and the free variables. Yeah, we can do that in a second term. Okay. Supplier phrase name. Okay. Okay, so promises. It's a list of promise. And we have name supply, which is a list, an infinite list of strings. Oops. We'll need more things, but one thing at a time. So start memo state. We'll manage promises start empty, name supply equals zip with plus first list is repeat $D, let's say, and the second is a one, blah blah. It's not happy. Oh, sorry. Yes. That should suffice. Okay. Can define the state of member state. That is silly. You knew this would happen. That's not. Which one is it? Is eval state? Not state. Right, that's the one I want. Okay. Now we need a few functions. So we need fresh name. Fresh name equals there's probably a one-liner with muck. That's not a very good name. Do state as using lens. I can just go to the lens and look. Oh, maybe it's use actually. There's a bunch of things. So. I guess there's just use and with this modify as well, right? Modifying. Right, so I can just get the thing. So I can do fresh supply use. I need it to be generic. Use name supply. Assign, is that the thing? Assign hash name supply return fn. Plenty of things will not work. Okay, so I need import thc.generics. Why identity? Oh yeah, because it's a state T, blah blah. That's also yeah, but there's no identity thing here. But actually, state is state T of identity, I guess, and the state T raises the monad fail thing. Okay. No, it's head and tail 4, right? I'm never sure. Or HDNTL. Boom. Okay. That's my fresh name. What else do I need? I don't know what that is. Okay. Okay. Then I need basic exists. For now, it's going to take a term, so that's how Ah, that's interesting. Well, these are states. Okay. But states don't have names. Commands have names. I won't be able to finish tonight. I'm so frustrated. But state. Yeah, we never need the binding until we'll later rebuild it, I guess. Markable. Okay. Piece of promise. So we say the name of the promise applied to map rn. Applied. Free variables of p. Well, we're saying that it's basically a function that we're applying, and so we need to apply it to several terms. Well, I mean, we would just, you know, match the pattern, abstract it. There's a bit of unification going on here, which is scary. Also, I don't understand. So we match a state against the meaning of P, and P becomes a term, I think. And that's what we do. We return a term. But here we're suffering a bit from the, which is what, yeah, that's what's supposed to do, but we return a command ourselves, and they don't have names. But we can abstract over a unit. At least kind of what they're saying here. We can abstract over a unit, and we'll. It's unrelated, but that gives us always gives us a term. Then we have to apply it to. It gives a computation, and then we apply it to unit. We can start with this. State that returns a maybe computation. So here we're starting to have a promise coming up. We will need promise name. could use duplicate record fields. Promise name, the string. And meaning is state. Exists do so we take the promises. And then we won't change it so we can return immediately. What we return is basically lookup state in the promises, and then I just apply view promise name to this. So I'm gonna have troubles, but ooh. Yeah, that's because it's maybe computational here. That is not at all what I expected to see. Oh, I see. Yeah, it's not because it's not lookup. It's a find thing. Find a hash is missing here. Oh, yeah. Okay, EQ state is more interesting. Boom. So exists is defined. We can probably do better, but whatever. And then we want promise. Let me promise a thing. I'm just going to take the arguments. So I take a string, the state. Oh no, I don't take the string. I just take a state. It's just going to give me a name instead. It returns m of computation, I suppose. I'm a bit shaky on this. So we need a new name. It's fresh name. We promise 0 x state, and then we turn call x, where promise 0 x state prime is $do. I probably don't need do. Modifying hash promises, and I do promise colon. We're getting there. Then I sort of have everything I need, maybe. Almost. I need to do the bindings, but at least we can see some things happening. So memo eyes takes a state to end computation and return a same. memorize of opt and of state equals do. So not really do, I don't need to. I can start with exists fresh lambda case, not fresh, exist st lambda case. So there's two possibilities. Yes, it exists, just res. So that's a computation, and I want a, it's not computation here, it's command. So I need to return the command, and so I'm going to assume for the time being that I can just do interact of res and unit. And in case there's nothing, that's where there's a bit of work to do. We first have to promise state. Then we evaluate state. I don't have the binders here to do add binders. And finally, we return what do we return? Promise needs to has return a computation for us. Res. It might end up being something slightly different. Ooh. Return. Woo. Dear Lord. Everything is $1. This is D1. Okay. So I need to add the binders. No bindings. Oh, we see we need a name here. Interesting. So this is really this returns. Okay. This must return a string. Oops. We will need it. And here, so we have res as a string, and here we have to do call res. And so bind takes a string and state, no, and what? state, I suppose, yeah. And returns m of unit bind of name state equals modifying hash bindings. We're adding a pair of name and case unit state. Oh, not state. FC case unit of Merklet defs C. I'm confused. Oh, I need to put muck here. Okay. Here we can do. Oh, but no, we get a command. Ah. So that's all fine. We can remove all the Merklet nonsense. Okay. And here we can do bind res e x. I can't read it otherwise. Okay. Now we need to probably do something about returning. We'll definitely need a third part on this. But now I kind of know what I need to research. Almost everything is there. I just need to read this paper in the companion paper extremely carefully now, because I know what everything is. So I'll read that for next time, and we can finish this quite possibly. It's kind of fun. So there's this. So I kind of need to extract all these bindings, yeah. And then we also, right now, we just make non-abstract terms, but what we really want to do is to have terms abstracted over their free variables and be able to substitute these variables somehow. I'll have to think about this. So just know that I don't care about the splitter. I'm guessing the run thing is the is where I need to do it. I've got a few ideas, but I'm trying to follow the paper. I'm moving a bit fast here. My guess is that when we exit, we just get all the binders and just add them. run scpm. So that's what they do. They have a specialized run scpm. That's really defined somewhere. Yeah, so it's specialized, so we can do the same. So the easiest way is to do so what I do is I run X and I run the command and I've got all the bindings, and so I get all the bindings using use bindings bees. That's after running C, of course, and then I'll run X to get a C, and then we can just return mucklet bc. Boom. It's really hard to see if anything makes sense here. Will kind of make sense. Okay. It is a bit curious. It's kind of what is expected. This has just introduces 15 different subterms. Of course, it ends with D1 because it has to. It's probably not correct because there seems to be bugs in the evaluation. Debugging this will all be very, very interesting. We can to debug that, we could do a bit of pretty printing. That would help a ton. We can give us a few items, like we can do some code thinning. If one of the D's ends up not being useful, we can not print it. We can remove them. That would actually be kind of useful because we can see what matters. What else can we do? We could pretty print terms as name terms, and we can use name terms as a transformation back and forth, so that we can read this a bit better. Yeah, still going to be a bit verbose, but yeah. And so what we want to do next, to-dos, debug for the map example looks very fishy. To do pretty print a little. To do remove unnecessary, like unreachable bindings. To do inline single use bindings. To do fix definition map to use I1 and I2 the return value. Goal, observe map fusion. That would be neat. There's something I can do. No, that's good. That's true. Okay, let's not. Okay, this is mildly better. To do named variable representation to write examples, to do name variable representation to pretty print examples. Okay. I think that's all. It is late. I am visibly sleepy. I guess these two things are kind of the same. If you see a binding that is used in exactly, like, at most one other place, then you can inline it. That's probably not too hard. Well, anyway, before I fall asleep in the august presence of my chat here, I think I'm going to wish everybody good night, or any other time of the day. It might be where you are. So I'm going to make a small comment here saying basic memo. It is pushed so that I won't lose it no matter what. So I think we're going to do one extra week on this. And whatever's missing next week, I'll do offline. But there's still a few things that need to be done. So my goal is to see map fusion happening, because one of the cool thing about supercompilation is that apart from just using a fairly simple cases, there's nothing really complicated about this. It's almost generic. Most of the things, I had a few questions because I just decided to use a sequence calculus for fun, and we can like we can refine the splitter quite a bit if we want to. There's a lot of refinement that you can do, but at the end of the day, you have a semantic that's specific to your language, and the rest is mostly syntax. Well, the split is also a bit specific to your language. So you see, oh, how do I push my whatevers? And I'm a bit like, some things I want to understand is why do we need to have bindings both in the monad? But I guess in the monad they're lambda lifted, so you don't necessarily want them to be I don't know. Like, but we have bindings both in the monad and inside the state, and that is fairly curious. I'm losing my train of thought. But the point is, at the end of the day, it's fairly simple. Like, so far we have 400 lines of code. We need a bit more. To be efficient, we would need quite a bit more, and we need also we would want to have a better termination principle, but that's a bit besides the point here. These are all like fairly easy to implement, and they give you some pretty cool things, including like deforestation of recursive calls, like of recursive functions. So you have map. You should observe map fusion. That means that if you have a map of a map f of map g should eventually, if we manage to do it right, reduce into a single recursive loop, which is equivalent to map of f.g. Yes. So that is my story for tonight. Next week, that will be video gaming, probably Cadence of Hyrule, because there's new stuff that I will probably want to show. If I'm not ready, I'll do something else, and I'll do Cadence of Hyrule in 2 extra weeks. 2 weeks from now, I hope, like, I don't have anything. I'm pretty sure I don't have anything. I'm looking now because last time I had an engagement and I didn't know that. Okay, yes, 2 weeks from now we'll do a third and final part on this supercompiler, and then later we will resume the mathy bits. They will connect at some point, maybe, somehow, mayhaps. In the meantime, it's pretty entertaining. That will help me have a fresher look when I get back to the Proof Assistant proper. So yes, that's all. That's me, and that's good night, everybody. So until next time, don't forget to stay curious.